Hey guys, welcome back to chapter 10. In this video, we are going to talk about our next simple gas law. We're going to talk about Charles' law. Charles' law talks about the volume of a gas and the temperature. Just as a quick reminder, that means we're holding pressure and the number of moles constant. So pressure and moles are constant, volume and temperature are changing. So what we see here with this graph over here is that as we move from left to right, our temperature is going to increase. And as we move from the bottom to the top, volume is going to increase. And what we see here is a positive slope. So what that means is as temperature increases, volume also increases. Increase the temperature, increase the volume, increase the temperature, increase the volume. So what we see here is that as one goes up, the other goes up. And if one goes down, the other is going to go down as well. So for Charles' law, the volume of gas and its temperature are directly proportional. So again, we see that mathematical symbol, volume proportional to temperature. And we don't have that 1 over because there's no inverse here. It's directly. So volume goes up, temperature goes up, volume goes down, temperature goes down. Very, very important piece here. What unit does temperature have to be in? It has to be in Kelvin. Has to be in Kelvin. Okay. So let's talk about why. What's going on here? Well, again, we're going to look at the molecules inside of these examples. So by increasing the temperature, that's going to cause those particles to move faster. If the particles move faster, we would expect more collisions with the side of the container. But remember, if we're looking at Charles' law, what is it that we're holding constant? We're holding the pressure constant. So particles moving faster would result in more collisions and a higher pressure. But to keep pressure constant, we have to pull the sides of the container away from those particles so that we maintain the same number of collisions, we maintain the same pressure. So as those particles move faster, they're going to need more room to move if pressure stays constant. The opposite is true if we cool down. So if we decrease the temperature, the particles are going to move slower. And if we didn't change anything else, that would result in less collisions, a lower pressure. So if the temperature decreases, we also have to decrease the volume, push the sides of that container closer to the particles so that we maintain the same number of collisions with those slow-moving particles. Real life example of this, I know it shows balloons here on the screen, but if you think about a basketball or a volleyball. So think about being outside in the afternoon, shooting some hoops with the basketball. Mom says, time for dinner, and you throw the basketball down and you run inside. Forget about the basketball, leave it there overnight. You come back to the basketball in the morning, and what happens to that basketball? Yeah, it's flat, right? So as the temperature decreased at night, as it got cool at night, the volume of that basketball also went down with that cool temperature. So that's a result of Charles' law. Opposite example, when I used to play sand volleyball. So we would have just, a bunch of volleyballs kind of scattered all around the court just in case one got away. And if we accidentally threw one of the balls to bake in the sun while we were playing with another one. So we threw a volleyball to the side of the court. It's sitting in the direct sunlight, baking in the sun. We go to pick up that volleyball to use it, and what does it feel like? Yeah, it feels like a basketball or a bowling ball, right? Well, why is that? When that volleyball was sitting in the sun, the hot sun, the particles started moving faster, the temperature increased, So the volume of that volleyball got bigger. So it stretched it out a little bit and it felt really, really hard. Okay, so just a real life example of Charles' law. We're going to do the same kind of thing with Charles' law that we did with Boyle's. So we're going to look at two different scenarios, some initial time, some final time, and we're going to compare those two different scenarios with numbers. So here is an example of the equation we're going to use for Charles' law. Because the proportionalities are different, right? Boyle's law was inverse, Charles' law is direct. Because the proportionalities are different, the formula is going to look a little bit different. So the formula is V1 over T1 equals V2 over T2, or divided by T2. And what have I highlighted and put in capitals and put exclamation points next to? The temperature has to be in Kelvin. If you do it in Celsius, you will get it wrong. And that is a direct challenge because you'll see some of these on the exam or quiz. So you have to convert it to Kelvin first. Okay. So let's dive into an example, and I'm just going to clear up this slide a little. Clear up this slide a little bit so that we have some room to work. So imagine you have 2.37 liters of a gas sample at 354 degrees Kelvin. If we were to cool that sample to 298 degrees Kelvin, what would the volume be if we kept pressure constant? Okay. So reading through the first time, I would mark it up. So I would say, oh, there's a volume, there's a temperature, and it's asking for volume. So I see a bunch of V's and T's. So that's how I'm going to locate it as Charles' law. Then I'm going to take, I'm going to take inventory of what I know and what I'm trying to figure out. So V1 and T1 and V2 and T2. So imagine we have 2.37 at 354 Kelvin. So that must be the initial. So 2.37 liters. 354 Kelvin. And we cool the sample. So we cool it down to 298 Kelvin. What would the volume be? So that must be what we're solving for. Okay. So I have three variables. Solve for one. Now we just need to plug and chug into our problem. So V1 is 2.37 liters divided by 354 Kelvin. And that equals V2 is what we're solving for, and we have 298 Kelvin. Okay. We have a fraction. Fractions are no fun, especially when the variable that you're trying to determine is on the bottom. That's not the case in this example, but it will be in other examples. So to get rid of the fractions, so that's going to be the first thing I do. To get rid of the fractions, I'm going to cross multiply. So cross multiplying is just multiplying on the diagonal. Doesn't really matter which diagonal you do first or second. The results will come out the same. So multiplying on the diagonal, so one of the diagonals is going to be this right here. So we would take 354 Kelvin, and we would multiply that by V2. And that's going to be equal to multiplying on the other diagonal. So the other diagonal is going to be this guy right here. So we would take 2.37 liters and multiply that by 298 Kelvin. So by cross multiplying, what that does is it very quickly gets rid of fractions. I don't like fractions. And it puts us into something that looks very similar to Boyle's law. So now to solve for V2, we simply divide by 354 Kelvin. On top, on bottom, that cancels. Whatever I do to the left side, I also have to do to the right side. And again, we see our units behave. So Kelvin on the top, Kelvin on the bottom. We're left with liters, which is good because we're solving for V2. Before I plug this into my calculator, I can predict what V2 is going to look like. So let's do that real quick. So here we see that temperature decreases. So what would we expect volume to do? Well, we would also expect volume to decrease. So after plugging this into our calculator, V2 should be something less than 2.37. All right, so let's plug this into our calculator. So 2.37 times 298 divided by 354. And the new volume we get is 1.99 liters. So does that answer make sense? Is that what we expected? Absolutely it is. So 1.99 is certainly a smaller number. That answer makes sense. You will be doing other examples of Charles' law where it will give you the temperature in Celsius and then it'll ask for the answer in Celsius. In that case, you would have to do a lot of conversions. So you'd have to first convert to Kelvin, get your answer, and then convert back to Celsius. So if you see any unit other than Kelvin, conversions will be a part of the problem. That is it for Charles' law. I hope you guys found this helpful.